I'm very pleased to welcome you to this, the second Academic Fall Forum, which we intend to be an annual and important event here at CU. As I trust you all know, a faculty task force 2 years ago called for a revision to our program review process. As a result, the campus has changed that process in a number of important ways. Changes seen perhaps most immediately in the fact that we are now looking at linked units simultaneously, so that this year we'll be looking at a group of departments and institutes in the physical sciences and mathematics. We wanted to start this year, and in fact each reviewing year, with a moment of reflection about what we do. That is, before we start counting student credit hours or worrying about what the curriculum in our undergraduate programs look like, we wanted to step back and ask some of the larger questions about the mission of the units under review and how those units can work better together. Now, I realize that many in the faculty are wondering why we even bother with program review at a time when we're constantly told that there are going to be budget cuts. People are concerned that a whole lot of work will go into a process that will have no results. Our hope is that we've redesigned program review in a way to be more focused on looking forward, to be less concerned with the immediate moment and the pressures of immediate budgets, and more involved in thinking where we are headed collectively. We do have a strategic campus plan in place, Flagship 2030, that has been embraced by the faculty. It provides us not only with a map of where we are going to be next year or in 2 years, but also glimpses of where we hope to be in 20 years. Program review is tied to that document as well as to more local planning documents, so we remain convinced that this process can help us move forward. Of course, the units under review this year have for a long time played a central role on the campus, and our hope is that this process can help us make them even stronger as we move forward. Now, this is a community conversation to which we've invited the entire campus, and I can see everyone turned out, and key players on campus are, and who have an influence on academic planning are here. The deans are here, the provost is here, various members of the campus-level program review committee are here, some internal reviewers are here, and so on. Most importantly, members of the faculty, the students, and staff are here to express their ideas about these units. We'll be hearing about the units under review this afternoon from leaders in those units, and we will close the day with a panel on some larger questions, including how should this particular group of units express their concerns to central campus audiences. Today's program has been structured by the faculty in the units under review under the leadership of Associate Dean Susan Beatty and Vice Chancellor for Research Russ Moore. Let me quickly say that there are two things we are not doing today. First, this is not about nuts and bolts. If you have a question about how the internal review process works, ask me later. This is not about process. It's about the work, the science that you all do. Second, we're not necessarily trying to answer any questions today. In fact, our goal really is to pose questions to ourselves as we enter into the review year. So some very quick things. There are bathrooms outside to both sides. Those of you that are doing presentations, this entire session is being taped for eventually going on to our very fancy website under design for program review for people who can't be here. If you have media in your presentation, you haven't given it to Bob in the back, please do so. We'll have a series of panels this afternoon. We will conclude with a reception to launch an exciting year of review. There will be wine provided by the provost, for which we're very grateful. And most importantly, I want to thank the person who puts all this together, Andre Grota, who does an amazing job of running faculty program review. Thanks for coming. So I'd like to turn things over now to the provost, Stein Stewart. I'd like to say a few words. Stein.
Thank you, Jeff. All of us are familiar with program review, how it's evolved over time. And of course, over the years, many of us, including me, when I was in a different job, would lament the efforts and the lack of necessary or wanted outcome and so forth. But clearly, things are changing, and this is what's taking place now. We're doing program review to make us better. We're involved in introspection, but also peer review on the outside to make sure that we know and the outside constituencies within the university are aware of the quality of what we do, the impacts, what we do well, strength, weaknesses, opportunities, the needs we have. Of course, in the past, when departments, units had needs, there were of course not much forthcoming, other than grief and promises of a brighter future at some point. But now we're trying to really put the necessities in place and link these in ways that Jeff has talked to make sure that things are relevant. You all put tremendous efforts into these things, and we want to make sure that it pays off, that you all support your unit, your department, your institute, and indeed there's a closure, that indeed there are things there that will be helpful for good or for a corrective action, so to speak, but things that will really help the enterprise get forward, make sure that we do what needs to be done in an open, peer-reviewed type of setting. So good luck to all of you. I'll sit here and listen a little bit, and then I'll get over to applied math a little later on, before Harvey here.
Thank you, Stein. We've next invited the two deans to whom these units report to speak for a few minutes to kind of set up a vision for us all as we move forward through the review years. So we'll hear first from the Dean of Arts and Sciences, Todd Gleason, and the Dean of the Graduate School, John Stevenson. Todd.
Thank you, Jeff. So I don't want to make John's job more difficult, but I'll just start out by saying the vision of the Dean's office is defined by the vision of the faculty and the departments. It's not my vision that's important to the extent that I have a vision. It's really how the vision is articulated from the faculty. And that gets me off the hook for the main theme of the talk. But it's a serious comment to the extent that I think an opportunity like this, which is actually very rare, for those of us in cognate departments to sit together and talk about common accomplishments and common aspirations, is a rare thing. That defines the vision for the next, it can define the vision of the individual units as well as the cognate grouping of departments for the next decade. And so this is an important opportunity, and we should try not to squander it. We are limited to some extent because not all the physical sciences are here. Like all of our departments and our institutes, we have a multidisciplinary spread under any of our umbrella headings. And so our colleagues in geology are not here. Our colleagues in geography are not here, and the folks in the life sciences that have commonalities with different areas of the physical sciences aren't here. That's not a shortcoming of the process. We've got to, package things in some reasonable way. This is a reasonable packaging, but we shouldn't forget our colleagues who enjoy the opportunity to go through this in a year or two. So let me toss out a few challenges that I think it would be fruitful for us to talk about, for you to write about in self-studies and in responses to the reviews, and to talk to the reviewers that come to campus in the next couple years. There are challenges that I don't believe are exclusive to the physical sciences. They tend to be challenges that in some cases are common to all of our disciplines, from art to astrophysics, but many of them are a consequence of the nature of the scholarship and the graduate training that we undertake in the bench sciences and in some of the physical sciences. Startup funding is certainly one of them. It's not how do we find the money. That's certainly an issue. But I think more important for a conversation among academics is how do we recruit the best people nationally and internationally and come up with a rational way of determining how much is enough. I think if you all, when department chairs talk to John or talk to me or talk to Sue about how much they need, none of you are going to admit that some of that money is I love you money. It's not money that's absolutely necessary to make that new faculty member successful. It's we love you more than Cornell, or we love you more than UCLA. How much is enough? Now, some of the chairs in some specific recruitments have developed very good ways of zeroing in on that, finding efficiencies. There are some best practices out there, and I hope you will take the opportunity to share some of those best practices. I say this not in a administrative self-serving way in the sense that whatever the total is, I participate. It's because whatever the total is, you participate. That every ICR dollar that you spend on a startup dollar is a dollar that you can't use to support purchase of common equipment or matching grants or research support staff in your units. And I think if you even set aside the notion of where do we get the money, I think it is worth us talking about as a group what are the best practices for finding the right amount. Facilities. The physical sciences are in space that in not every case you would call contemporary. And if we are going to maintain our position, which I believe is in the upper third or the upper quarter of our peers nationally in the physical sciences as a group, we have to figure out a way of maintaining not only contemporary space for our faculties, but also contiguous space. The lack of contiguous space is an issue that occurs on every university campus as programs grow. You begin to develop satellite programs. And while there is value in having intermixing of scholars, there is some price paid to a unit for losing its contiguous nature. And I would love nothing more than to see a group of chairs and directors sit down and horse trade space in order to try and address some of those issues, rather than have Keith Maskus or Bill Kempfer or somebody come in with a stick and do the same thing. There are organizational barriers that I believe would be worthy of conversation. If we were to have held this forum 5 years ago, and we were talking about what kind of organizational barriers do we experience, we would the topic of recruitment of institute department faculty and how we deal with them with regard to reappointment, tenure, and promotion would have been on the list. I may be deceiving myself, but I think we've done a much better job over the last 5 years of ironing out some of the wrinkles in our organizational structure that disadvantage some of those joint hired individuals. Hiring, we probably still have some work to do. It is every year that it seems that deans kind of find out rather late in the game what institute aspirations or even what searches they're engaged in, and that institute directors find out rather late in the game, if they're not in that particular department, what kind of hiring is going on in some of the cognate departments. And I think we could do a better job and hopefully a little bit more efficient job of hiring if we shared more information. There also is an inherent organizational barrier in staffing that each of our departments and programs have accountants. We each have HR specialists. We each have IT personnel. In the last budget exercise, the College of Arts and Sciences, while leaving the physical sciences and life sciences pretty much untouched, we consolidated a lot of services in the social sciences and humanities. We created financial centers. Not an original idea. It actually derived from a conversation about how Ceres works. And and if you look at Ceres has some centralized functions, as do some of the other institutes, that really provide efficiency and which you may think means saving dollars, but it actually means much better service and much more professional service. I think the physical sciences, particularly those that are near neighbors in a physical sense, have an opportunity to find some of those same kind of efficiencies and share staffing resources in key areas in such a way that it allows you to take some of your discretionary dollars and reassign them to either the training, instructional, or research missions of the department, which I would argue are more important things to be spending dollars on than each having your own, whatever. I hope you have the opportunity to talk about that. Graduate program participation. This is a problem that I find to be more of a problem in the humanities and actually the social sciences than on the natural sciences side. But if you think about what our roles are as academics at an AAU university, where we are supposed to be defining the cutting edge, and we are responsible for moving the boundaries of new knowledge and new procedures and new techniques, there is no better way for us to do that than through our graduate programs. That in some ways, those of us who are in tenure-track faculty lines are, we know what we know how to do what we do, and we can be very good at training students in those skill sets. And although all of us evolve as scholars and researchers over the years, I don't mean that we're all stuck in the same technique throughout our careers. There's much more opportunity to move our fields ahead through our graduate students. It's kind of, what is the purpose of a department? Is it to perpetuate our expertise, or is it to make it obsolete? And is the knowledge and the areas that we research, is the purpose of our lives to perpetuate it, or is it to get it into the introductory textbooks and move on to something else? I think there is no better way to do that than through our graduate students. That is the seed corn for the next generation of academics. And just like the farmer who will fail if he only plants the same variety of seed year after year after year, I think it's our role as academics to experiment with those hybrid vigor characteristics of some of the new strains. How do we do that as academics? I think one of the ways that we can do that is for us to consider opening the doors to our graduate programs to our neighbors and other departments. All of you have had graduate applicants who, although let's say they may be a physicist applying to the physics department, may in fact be better trained to the requirements of applied math, or to the math department, or to APS. And while we're willing to move students around to some extent, or put an applied mathematician on our graduate programs, why is it that we are so resistant to having an applied mathematician chair a committee in our department, if that makes sense, and vice versa? There should be, it is something like an open enrollment concept that I'm thinking about for participating in graduate programs. And it creates the opportunity for a high degree of cross-pollination that I think allows us to satisfy what I think society's expectation of us is in terms of moving our fields forward and making those old ones obsolete. Among my other list of challenges is graduate recruitment. As I visit programs year in, year out, probably the most frequent, I don't want to say the first issue that comes up, but probably the most frequent issue that comes up is the issue of graduate recruitment. I think moving our departments to the next level, whatever the next level happens to be, is to some extent dependent on how creative and novel and energetic our graduate population is. Those are the folks, in some ways for the same reason I'm talking about cross-pollinating our graduate programs, those are the folks that I think make us better and make our department's reputations better. And this one is, the key characteristic is often graduate stipends. We have a caliber of faculty in the physical sciences that I think can recruit the very best graduate applicants nationally and internationally. I don't think that's the bottleneck there. Those students, perhaps wisely or perhaps naively, are following the dollars, and somehow we have to come up with some way of addressing that, because it is in our interest to recruit the graduate students that have the most experience and have the most initiative, and those are the students that those are the ones we most remember when we talk about our graduate recruitment failures year to year. That is a problem. That is largely a dollar problem. With regard to dollars, all of these can be solved by more money, startup funding, facilities, more staffing, et cetera, et cetera. And for those of you that attended the chair and director's breakfast this morning, you heard Rick Parecka say we shouldn't retune our aspirations because of the temporary economic times. I think that is true, but if we limit ourselves to thinking about the expensive and the highest aspirations, and we don't spend some time thinking about what we can accomplish with the resources that are going to be available to us in the next 2 or 3 years, we're going to look back 6 years from now and decide that this process was a failure. And so while Rick's statement this morning, I think, is philosophically correct, I think operationally we need to think about what we can do with the resources that you have and that the campus has in the relatively short term, so that we can feel we can move ahead on some of these areas. Finally, and I won't dwell on it very much because I think it's one of the targeted topics of conversation in the panel this afternoon, is the role of campus-directed initiatives versus hiring aspirations within the departments. I think that is something that the physical sciences, perhaps more than most of the other areas of the campus, have been subjected to the pull and tug of those sometimes differing priorities. That investments in our foundation is much less sexy than the new thing. And taken to an extreme, that can hurt the pillars upon which we build our interdisciplinary research and that we build our institutes on, and that is functionally important for the long-term health of our departments. And so I hope there's some productive comments that result from those things. So those are my comments about no vision, but recognition of the challenges. And I would encourage, historically, I've been involved with program review for a long time in one form or another. One of the shortcomings that we have when we go through the process is that we don't spend enough time talking to each other, and spend probably too much time trying to defend our disciplines. The list of people that are participating in this review don't have to worry about defense of their disciplines. This is not the group that, the campus is looking to when they think about, well, if we have to do without something, what is it we do without? Don't worry about defending your disciplines, doggone it. Spend some time talking about how you can make them better, and a lot of time about how you can make them better in partnership with your cognate areas next door. Thank you.
Thanks, Todd. Thanks, Jeff. Thanks to all of you for coming out today. I see we're already behind schedule, so I will try to keep my vision brief and to the point. But there are a few things I want to say about graduate education on campus in general and about graduate education as part of the review that you're all undergoing this year. You'll recall that the Flagship 2030 famously summarized its aspirations for graduate education on this campus with the terse phrase, enhance graduate education. Since the recent memo from FactMan about enhancing trash pickup, I've been a little alarmed about what enhancing graduate education might be, but I'm going to stick with my original understanding of the phrase, which is that this campus wants to both increase the size of graduate education and increase the quality of graduate education. And certainly the quality of graduate education that goes on in the physical sciences and the units represented in this room is some of the very best graduate education on campus. And so I would second everything that Dean Gleason has said about the importance of cross-pollination, about the importance of finding ways to recruit the best students, about finding ways to be flexible in the way in which departments work together to train the next generation of scholars, researchers, to train the intellectual leadership of tomorrow. And I'm anxious, as Dean of the Graduate School, Interim Dean this year, to work with you on that. There are a few specific points that I wanted to bring up for you to keep in mind as you begin to think about your own unit strategic plans and your own cross-unit conversations this year. One, it's been, I think, almost forgotten, but all the work that you did a few years ago for the NRC may actually produce a final NRC report sometime in maybe this fall, but certainly probably this year. Lou has a slightly more cynical view of the womb in which this particular child is gestating and the kind of how long that gestation period is. But I suspect it will be out soon, and I think the timing could not be better, because I think a number of your units will come out of that review looking extremely good indeed. And I think you can use the kind of information that NRC provides and the kind of comparative data that it provides to really understand your own excellence and be able to sharpen your plans for the future in terms of your own graduate programs. The other thing that I would recommend that you not forget, one thing that makes this place very special indeed, in addition to just the kind of quality that Todd was talking about, is that this campus is fairly rare in the way that it thinks in its STEM disciplines not just about research but also about teaching. Not just teaching for its faculty, but also training graduate students to be better teachers as well. We have enormous energy on campus, great ideas for thinking about STEM education and the involvement of graduate students in that effort. And as you formulate your plans again and conduct your conversations, I think you should not neglect that side of it, thinking about graduate students, thinking about their potential futures as faculty members who are teachers as well as researchers and your own teaching programs. I think that a lot of the people in this room are the faculty who are most interested in our relationships around the world. And as you know, one of the primary initiatives in Flagship 2030 is to turn us into a global crossroads. I would say we already are a global crossroads. If you look around campus and you look at the number of international students, you look at the exchanges, you look at the kind of research collaborations that are going on, we really already are an extraordinarily active site for international connections. But as some of you know, but maybe not all of you, there is a task force doing work right now. Larry Bell from Office of International Education, myself, are co-chairing that, and we're working with the American Council of Education on what they call their internationalization laboratory. We're very close to producing a draft of a strategic plan, and I think that plan will offer a number of solutions to some of the problems that I know you all face in working internationally. And so I'm very hopeful that we will, some of these have resource implications, but some of them don't. And I think all of you in this room understand what a benefit it was when we were able to change the tuition policy for international students a few years ago, and I'm hoping that we will make a number of other changes that can have the same kind of impact. And so I think, again, as you conduct your conversations and write your plans, keep an eye on the international aspect and look for this report to come out this year and see how you might be able to use some of its recommendations to further your goals internationally. Todd talked a little bit about how disciplinary boundaries can they obviously enable a great deal of the work we do, but boundaries always limit as well. And so I think one of the things that I'm most interested in is seeing how we can use the fabulous interdisciplinary work that takes place on this campus to think about new kinds of graduate degrees. I've talked to a number of you already about some professional science master's degrees, and certainly there's a lot of conversation around the country about those, and I'm very excited about that idea. But I don't think in our rush to develop the professional masters, I don't think we ought to neglect our responsibility, say that 6 times real fast, responsibility to develop new interdisciplinary research degrees as well. And for those of you who have ideas about that, I certainly am more than willing to sit down with you and think about how we can do that. So those are just a few of the things that are on my horizon. I think the word vision is one that I have a little suspicion of. You know, it's overused, and every politician gets asked, well, what's your vision? And I'm still waiting for somebody to say, well, it's about 2030 with a touch of astigmatism. But I think that vision does have a double meaning that's worth keeping in mind. Vision has come to be this almost woo-woo notion of the future and the pastures of plenty that are ahead, but vision really is about seeing what's in front of you. And I think program review is a wonderful opportunity to both think really hard about what's in front of you, see it clearly, see it whole, but also to think ahead, think about what the future might look like. And it seems to me that those two processes, rather than being separate, are often much the same process. And so I just recommend to keep that dual sense of vision in mind. So I've gone on long enough. Thanks very much.
Well, thanks to the deans and the provost for being with us today, and we appreciate their leadership throughout this review process. We're now going to turn things over to Sue Beatty and the first panel, and we'll get things going.
Very brief introduction. The 8 units that are undergoing review are well-known, well-regarded, highly ranked nationally and internationally. And I believe after you see these short presentations, you'll understand why that is. I'm going to introduce each one, and hopefully we'll have a bit of time for questions after each presentation. I have promised I won't drag people off with a large hook, but I'm going to try and kind of keep things on schedule, so about 15 minutes for each unit's presentation. So we'll start off this with Professor Harvey Seager, who's in the Department of Applied Mathematics, who's going to give us some information about what they do in applied mathematics in a way that we'll actually understand.
So I want to thank you all for allowing me 10 minutes to come up here and brag about our department. Let me start first with some just the basic numbers. There's 16 tenure track faculty. We have 4 rostered instructors. We have some number of lecturers, and based with that staffing, we taught more than 15,000 student credit hours last year. So we all agree that our teaching load is heavy, and we've whined about that for years. I'm happy to say that just a little over a year ago, we got an additional faculty position, and we're searching for another one now. So whether we'll be able to continue whining about that is not so clear. I want to also talk about the organization of the department, because it's as confusing as possible. The faculty are in the College of Arts and Sciences, our undergraduate majors are in the College of Engineering, and our graduate students are in the graduate school. So if that seems a little crazy to you, it's because it's a little bit crazy. But there are advantages and disadvantages to having that structure, and I'd say the biggest advantage is applied math is interdisciplinary, not only because of the way we're organized, but because of our intent. And that's going to be a theme I hope you'll see throughout this whole presentation, is how we do things in an interdisciplinary way. Let me first tell you about our teaching. There's 2 points I want to make. First point is, year after year, our best graduating seniors are just phenomenal. And I'll give you 2 examples of 2 people who graduated last spring. This is Max Moe. He has a double major, one in applied math, which puts him in the College of Engineering, and the other one in astrophysics physics, which puts him in the College of Arts and Sciences. The College of Engineering voted him the outstanding graduate for research last year because the guy had published 8 papers in astronomy before he graduated from college. He started in graduate school in astronomy at Harvard now, more or less. This is Eric Eason. He also had a double major, one in applied math, one in engineering physics. He won a Hertz Foundation Fellowship. I think a lot of you know what that is. For those of you who don't, I just got an ad for them in the mail yesterday telling me to apply for somebody, send our new students in. It says, for innovators in the applied physical, biological, and engineering sciences. So the people who are here is basically who this applies for. The Hertz Foundation gives out 15 or 20 of these every year across the United States. And they cover all your graduate student expenses for up to 5 years. So it's a very good deal. And the fact that Eric won one of those means that he was not only one of the top students at CU, but he was one of the 15 or 20 top students across the United States. And by the way, he did all that just before he turned 18 when he graduated. So he was an amazing kid. You'll notice both of these students had majors of applied math and something else, and both of them went on to graduate school in something else. Among our stars, some of them stay in mathematics, some of them go into other disciplines, and both of them are fine with us. Our objective is to get students to develop their talents. It's not the case that we made these guys smart. They came to us smart. What we try to do is provide them opportunities to develop their talents, and these two examples show that some of these students do that very well. Okay. The second point I want to make about teaching is a procedure we're using to try to improve our instruction in calculus. So that's the basic course for all the engineers, for all the scientists, and so on. Let me tell you what the problem is. It's not a CU problem, it's a national problem. Across the United States, 40% of all college students take Calculus 1. And of those students, 40% of them fail. That's an appalling statistic. The statistics in our department are slightly better than that, but are still bad. It's like 30 to 35% year after year. So we've been working on trying to change that, and we've done a bunch of things over the years. I can't tell you about all of them. We have an assessment exam which is given out the first week of class for the freshmen, and it tells, well, it's all about do you know algebra and trigonometry, and it's the best single predictor of what your grade will be in calculus. And then starting in 2006, we started using a program spearheaded by Mary Nelson, whose pictures you see there. She's one of our instructors, to have voluntary ungraded orals before each written exam during the semester. I can't tell you how those work, but let me tell you what the outcome is. This is a graph. Each yellow and green stripe is a segment of the population of students based on their scores on the assessment exam. So the ones way over on that side are the ones the assessment exam says are liable to fail. And the ones who took no orals are in the yellow. Their grade point average was 0.5, so it was halfway between D and F. And the ones who took 3 orals, their average grade point was 1.7, which is basically a C-, so they barely passed. In each one of those segments, what you see is no orals versus 3 orals raises your letter grade by about 1 letter grade. It's really well, we're very happy with the outcome of this, and we're pushing this whole idea into new areas. So now let me tell you something about our research. I'll give you some current examples. I'll talk about where I think the area is going, and then we end with what resources are needed. So this is a picture of Mark Hofer. He was one of our graduate students. He graduated in 2006. While he was a graduate student, Peter Engels was a postdoc in JILA. He was working in the lab of Eric Cornell, and he was exploring some of the properties of Bose-Einstein condensates. And what he was doing was creating shock waves, blast waves, and he wanted to see how they looked in a Bose-Einstein condensate. So the picture on your left is a photograph of an experiment. There was a blast wave. Bright in there shows high density. So there's dark in the middle because there's no condensate left because it got blown away. And then there's a bright ring, and then followed by all these oscillations between bright and dark and bright and dark and bright and dark. And those oscillations don't show up in standard shock waves. And they couldn't figure out what that was all about. It was a puzzle. So Mark Hofer and Mark Ablowitz went over and talked to them. And the important information is there are actually 2 kinds of shock waves. The standard kind doesn't have these oscillations, but under the right kind of conditions, you can have shock waves which are controlled by dispersion rather than by dissipation. And the picture on the left is a numerical solution of the Gross-Petayevsky equation, which is the standard model for Bose-Einstein condensates. And you see that they have the same oscillatory structure. By now, Peter Engels has left. He's at Washington State. Mark Hofer has left. He's at North Carolina State. They are continuing to collaborate with each other. So this example is a great success all the way around. Second example is work done by Manuel Lietzer, who is sitting right there. He worked with Rob Knight in chemistry and biochemistry, and I'll tell you what the problem is. I have a stomach ache. I go to the doctor and say, I have a stomach ache, and he takes some samples from my intestine to find out what's going on, and he finds some microbes, various kinds of microbes. He finds M of them. And then the important question that they were wondering about is, what fraction of all the microbes in my stomach do we actually have? And you have to figure that out without knowing how many microbes there might be. So there's an unlimited number of microbes possible. What fraction is M? If M is half of them, we better take some more samples to get a better idea of what's going on. If M is 95%, then maybe we can proceed. So by using statistics along with the other stuff they were doing, they were able to get an answer to that question, and Rob Knight is now using it in his biochemistry lab. The third area is scientific computation. That's a big deal for our department because more than half of our faculty worry about scientific computation. I see Sue's standing up over there. I think I can skip over this to try to stay on schedule. Pretend that you were impressed by those last two slides. So the question is, what is the future of research in applied math? And here I don't mean just our department, but in the whole subject of applied mathematics. So one of the things is there'll be new problems coming along. The new problems will need new methods, and they'll need new models, and so that will go on. That's just sort of what we do now, and that will continue to go on. But there are two other things which are going to be new. They're coming into fruition now. One of them is working in very high dimensional spaces. So in lots of situations, an increasing number of situations, we can now get lots more data than we ever used to be able to get before. And then the question is, how do you process that data? How do you get meaningful information out of it and not just lose stuff? Genetic microarray, for example, gives you information about 2,000 genes all at once. If it has a 1% error, that means it gets 20 different genes wrong on the average. And if one of those 20 genes is exactly why you did this test, then you're dead. So how to process that information is going to be an important question in the future. Another important question is virtualization of scientific problems, in which the best model we will have of what's going on in some process will be a computer model. Astrophysics has been in this situation forever. They could never say, what happens if we take this star and move it over there? They had to have theories, and then there were a few observations. But that's going to be more and more important, where we don't have good laboratory experiments. We have to rely on the computer simulations. And how do you do that without getting burned badly is going to be an important question. So then the last question is, what about resource implications? That's what PRP is all about. And so the question is, what new resources will applied math need to carry out its mission? That's a great question. I'm not going to try to answer it here because that's the whole purpose of the PRP study is to go through all that. So when we have our self-study, then we'll give an answer to that. That's the end of my presentation.
I'm Paul Beal, chair of the physics department. Physics consists of 50 tenured and tenure-track faculty and another 12 adjunct faculty in JILA. According to the U.S. News and World Report reputational survey of physics departments, we have the 10th best physics department in the country at a public university and 20th overall. And that same survey ranks our atomic, molecular, and optical physics program that's in physics and in JILA as the best place in the world to do atomic, molecular, and optical physics. Our research areas span just about all of the major subfields of physics, and I will be hitting some of those later. Just wanted to show some of the awards to physics faculty in recent times. 3 Nobel laureates, 6 members of the National Academy of Sciences, 2 MacArthur Foundation Fellows, 4 members of the American Academy of Arts and Sciences, Packard Fellows, 2 distinguished professors, 2 presidential teaching scholars. John Warr won Professor Distinction Award this year, and a Hazel Barnes Prize. Our physics faculty, many of them have joint appointments with other CU institutes and national laboratories, most notably JILA, Ceres, and LASP, and a number of our faculty also have very close appointments and relationships with NIST Boulder and with the National Renewable Energy Lab in Golden. So we very much pride ourselves on our research excellence. So we have some photographs of some of our faculty. So this is Eric Cornell and Carl Wyman, who won a 2001 Nobel Prize for the discovery of the Bose-Einstein condensate. Jan Wahal, 2005, for high-precision laser spectroscopy. Margaret Murnan is a specialist in femtosecond high-power laser systems, member of the National Academy, won the MacArthur Award. Noel Clark won the Buckley Prize. That's the highest prize in condensed matter physics for liquid crystal research. Al Bartlett is still doing an extremely great job. I just saw him yesterday. He won the Global Media Award last year for excellence in population reporting. Debbie Jen's a MacArthur Fellow. She specializes in cold atomic gases. Jun Yi won Robbie and Bessel prizes in recent times. He is a specialist in high-precision laser spectroscopy and laser-based atomic clocks. Henry Kapteyn is another specialist in femtosecond lasers. Bill Ford won the highest prize in high-energy physics. Mike Dubson won the highest prize for undergraduate physics teaching from the American Association of Physics Teachers. Stephen Pollock is Presidential Teaching Scholar. And John Warr won a Professor of Distinction Award from the College of Arts and Sciences this year. Extramural research funding in physics this year is $23 million. That's spread across physics and faculty that are in arts and sciences but are also associated with JILA. Then there's the folks in JILA who are NIST employees, the 12 fellows I mentioned. We have the Center for Integrated Plasma Studies, connections with Ceres and LASP, so it's a total of $23 million. And as you can see, that's been growing very, very steadily over time. We're just as proud of our teaching excellence as we are of our research excellence. We've won many faculty teaching awards. We are the campus, in fact, national leaders in peer learning, interactive engagement, and guided inquiry in the undergraduate classroom, both at lower division and now at the upper division level. We run teaching and learning assistance training programs to make sure all the students who are in our classes have good access to our graduate students and students who just took that course a year ago. Those tend to be very successful at helping our undergraduates learn physics. We have an outstanding graduate research program, and we are leaders on campus in Science Education Initiative, CU Teach, which is designed to create more science teachers, and the iSTEM program that just got started. We have 3 majors that we work with. We have a Bachelor of Arts in Arts and Sciences, a Bachelor of Science in Engineering Physics, and we share the Astrophysics bachelor's degree with the APS department, so that's 350 majors right now. That's the 5th largest undergraduate physics program in the nation. That's both public and private institutions. We also have the 5th largest graduate program in the nation with 200 doctoral students. And that's shown, those 2 programs have both shown about 75% growth over the last decade. Just worth pointing out here, we teach 2,700 graduate credit hours. That's about 10% of all the graduate credit hours taught in the College of Arts and Sciences. We're very proud of our research programs for undergraduates. 23% of our physics majors do an honors research project, write an honors thesis, and have graduated cum laude, magna cum laude, or summa cum laude. Max Moe and Eric Eason, that Harvey mentioned, are both summa cum laude graduates from last year. Half of our graduates this past semester, that's both in physics and in engineering physics, graduated with Latin honors. We're very proud of our service and outreach excellence. The CU Wizards program has been in place since 1976. Saturday Physics Series for about 7 years. The Physics Education Technology Project creates virtual laboratories that can be used in science education K through 20. The George Gamow Lecture Series and the Physics 2000 website also is the attempt to teach modern physics to a wide range of students. We've won several important group and departmental-wide awards. We're very proud of having been ranked by the College of Arts and Sciences this year as the best department in both research and in teaching. We won the award for the best graduate program in the CU system last year, and the FET website has won 2 national awards. So I just wanted to show some pictures of some of the research that goes on in our programs. I'll try to highlight one on each slide. This is a quantum state predicted by Chris Green for what's called a Rydberg molecule. It's first observed this year. It got a lot of press in the physics community. This is data from Debbie Jen's lab showing the Bose condensation inside a Fermi gas in her experiment. A little creature down on the right here is a happy Bose-Einstein condensate from Eric Cornell's group. This is actually the Nobel Prize-winning data from 1995, paper by Mike Anderson, Jason Ensher, Mike Matthews, Carl Wyman, and Eric Cornell, which shows the development of Bose-Einstein condensate at 50 nanokelvin, 51 billionths of a degree above absolute zero. We have very strong programs in the optical sciences, mostly also in JILA. Precision metrology, that's mostly also in JILA. This is Junyi's atomic clock. It's the most precise atomic clock in the world based on strontium, laser-based strontium system. We have very strong programs in condensed matter physics. This is from Noel Clark's Liquid Crystal Research Center. Nuclear physics with big experiments at Brookhaven and in Germany. High energy physics has a big program with the Large Hadron Collider in Geneva. This detector here is the compact muon solenoid. In that field, that means it only weighs 12,500 tons. We're very proud of our geophysics group with a large number of major papers in recent times, particularly about the melting of glacial ice. These papers were then highlighted inside this copy of Science. Plasma physics, we're building a Colorado Center for Lunar Dust and Atmospheric Studies in the Nuclear Physics Lab. CU plasma physics spans physics, astrophysics, LASP, and engineering, and it's ranked, CU plasma physics overall is ranked 10th in the country in the same reputational study. Physics education research is a rather new group, but it's become very influential in the campus and nationwide. So they do a lot of work on trying to understand how students learn science and how to improve that in the classroom, and we use those, and this study shows some of our changes in intro physics have doubled or tripled the amount of learning that goes on compared to a traditionally taught class. We have groups in biophysics and also in history and philosophy of physics. So our students go to all sorts of different fields, not just science. But our most famous recent graduate is Hosea Rosenberg, who won the Top Chef Award this past year. He loved physics before he found his true passion in the culinary arts. The challenges, one of the challenges Todd mentioned is space. This is Dwayne circa 1972 when it was built, and this is Dwayne today. The only addition is the S-wing of JILA. And the faculty and students and staff are all in exactly the same physical plant they were in 1972. Startup budgets are another item that's critically important. Those have tripled or so in the last decade. Currently, a new faculty member might take many years to pay back, as it were, through the DIICR method to the department. And I'll point out, there is no ICR stream that goes back directly to Arts and Sciences or the Provost's office, who also help with those startup packages. So opportunities, our national reputation has grown enormously in recent years. We have a definite shift in our peer group. We now have to compete against places like Caltech, Chicago, Maryland, Texas, and Minnesota for our recent hires. But this provides us an opportunity to maintain that momentum and expand in our areas of excellence. We also have a lot of companies that are created by our graduates and faculty in the area, and that also provides an opportunity. And I just wanted to thank you and point out that Hosea did not cater lunch today.
Good afternoon. I'm here to introduce what JILA is and what JILA does briefly. This is the JILA building. It is on campus, as Paul suggested. It's physically connected to the physics building, which is a great thing for all of us. We can transfer back and forth there. There's a lot of people movement and technology movement and so forth. JILA began in the early 60s with the JILA Tower here, which was at the time compared to the postmodern pickle jar. There's a lab wing here, and over here is Dwayne Physics. In 1980s, JILA got a south wing added to it, and that will become important later on. In 1961, JILA was founded as the Joint Institute for Laboratory Astrophysics, and you can imagine, back in those days, at the beginning of the space race, how exciting that was, that there was a laboratory dedicated to studying the physics of outer space, and in particular the upper atmosphere. But you know what? These days, the scientific interests of JILA have broadened so much that we don't call it that anymore. It's just JILA. But we remember that it's a joint institute, and that's very important. I like to say also that we enjoy spreading our activities to the rest of the world. We have an extensive website. It's undergoing a major overhaul now, and come next year, you will be able to read even more about JILA on the web. JILA sits at the intersection of lots of different departments and entities. It's a joint institute between the university and NIST, the National Institute of Standards and Technology. Within JILA, you will find many things. There is a component of NIST. You know that NIST has a sort of branch office down the street here in Boulder. The main thing is in Maryland, of course. NIST's Quantum Physics Division is housed within JILA. On the university side, there's a large component from the physics department, as Paul just alluded to. There are chemists within JILA. There are astronomers within JILA, people belonging to the APS. Most recently, there are now people from MCDB who live in JILA and work in JILA. And I should say that within this boundary, there are something like, I don't know, 27 or 28 JILA fellows is what we call ourselves, the principal investigators. And we can point to each other and say, oh yes, this one works for NIST, or this one's in chemistry or whatever. But in day-to-day interactions, it really doesn't matter. There's a kind of seamless integration there. You can knock on anyone's door. You can stop anyone in the hall, and it's just a great place for doing science. And I think it is that because it's the intersection of all these things. And one of our main goals pushing into the future, one thing we hope to come out of this program review, is to keep our great connections with all these different entities that make us up. What goes on in JILA? The fellows of JILA publish, I don't know, 600 or 700 papers a year, something like that. Here I'll go through them one by one. If there was one activity that could be said to unite all of JILA, a sort of common theme that gets not everybody, but almost everybody, it's optics and lasers. JILA is a place where cutting-edge optical technology is developed all the time and put to good use for things. Just to go through a few examples, Paul alluded already to ultra-cold physics. It is a strange but true fact that you can actually take a gas of atoms and make it colder by shining laser light on it. And you can make a gas, as is done in JILA, whose temperature is measured in the billionths of degrees above absolute zero, where quantum mechanics is right there in your face, and you see things in a way you've never seen before. In addition, Paul also alluded to this. A great way to use lasers is to make ever better clocks. Right now, the United States runs on a clock which is housed here at the NIST facility. There's one that's just as good at JILA. There it is. And it's going to be better real soon, and it might become the new time standard. There are lots of good reasons to have ever better clocks. We can go into that if anybody's interested. There are ultra-fast lasers developed at JILA, so fast that you can imagine turning on the light and off again in, roughly speaking, the time it takes to form or break a chemical bond. It's like using these lasers to open up molecules and ask them, what's going on during this chemical reaction? There's a lot of work going on in there. It's part of our component of the strong chemical physics program, which really looks at chemical reaction dynamics at the most fundamental level possible. We want to understand what is it really that makes chemistry go. On the other hand, basic chemical physics works on very small molecules that you can wrap your head around, but JILA also has a biophysics program looking at molecules like this. I have no idea what that is, but it's supposed to represent some biologically relevant thing. You can probe that, as Ralph Jimenez does, with lasers in ways that are novel and unique. I should not leave out the fact that there is a strong astrophysics component within JILA, and they make perhaps the prettiest pictures of them all. There are people in JILA who work on black holes and supernovae and the formation of the solar system, lots of good things like that. Here's a terrific picture that I love very much about convection inside the sun. How cool is that to study? And I've left out some things, but as you can see, the slide is full. Is JILA any good at doing these things? Yes, I would argue that they are. Paul alluded to this also. I'll just run through a quick list of the major awards that JILA has. 3 Nobel Prizes, 2 MacArthur Genius Grant recipients, and 7 of the members of the National Academy of Sciences. And there's an interesting way to look at this. If you look at the number of women physicists in the National Academy of Sciences, JILA has 1/3 of them, which sounds great until you recognize there are only 6 altogether. Okay, we're still awfully proud of that. Paul pointed out that our graduate program is perennially rated #1, which brings us, in fact, to education. It is an interesting fact that though half the people in JILA are NIST employed, they're not employed by the university at all, nevertheless, they teach in our departments, and some of them are pretty good at it, actually. And you can get, for example, classes in advanced optics that the NIST people have special expertise in that enrich our programs over there. In addition to that, we have outreach activities. We are active in the CU Wizards program. Here's David Nesbitt, who in fact is a JILA fellow who runs the Wizards program. He's doing a chemistry of cooking demonstration there, which is awfully popular. We go to public events. Here's Heather Lewandowski at a sort of Meet the Scientist event at the 29th Street Mall. She's making ice cream out of liquid nitrogen to emphasize ultra-cold physics. You get the impression that we must eat well over at JILA. The outreach that is perhaps the most significant is that we go out and we interact in the schools. We have a program whereby our students and postdocs and faculty go into the schools in the Boulder area, in particular the economically underprivileged schools, and give the students their chance to do experiments and see what science is like. We're very excited about that. I cannot talk about JILA and how great JILA is without mentioning the JILA staff. JILA would not function without the staff. Sadly, it is not just a bunch of us eggheads sitting in the ivory tower that is JILA and thinking the great thoughts. Stuff needs to be done at ground level, and here's a nice picture of the staff. They've just received an award there for meritorious work on our behalf. There are lots of examples one could give of how great the staff is at JILA, but I think the most important thing I can come up with now is that here in the shops, button doesn't work, here in the shops, JILA has world-class shops and could not do the science without it. One story to relate is that back in the early 90s, when Eric Cornell and Carl Wyman were doing the work that led to their Nobel Prize, how did they get it done? Well, okay, they're first-class brilliant intellects, okay, great. But the other thing is, they had to have very specialized glassware. These things, these experiments take place in glass cells that are under super ultra high vacuum, and JILA is one of the few places in the world with the expertise in the shops to do that. And if you don't support the shops, you can't do things like that. It's a very important point, and we at JILA try to acknowledge that every time we can. We're very proud of our staff. I'm going to say something now that is, of course, common to every department under review here, being represented here. They are stretched to their limit. JILA gets bigger and the staff doesn't quite get bigger at the same rate, if you know what I mean. But bless their hearts, they're plugging away for us. I want to finish with an interesting topic here also of great interest to lots of the departments under here, and that is space is tight. Have you heard about that? I've heard a few people sort of tangentially refer to that. Space is tight. It's tight in JILA as well. I probably don't need to go through these things. The graduate students, who are the ones who really do the work, who do the research work, don't have a place to sit, not all of them. The lab space is committed. That affects new hires. The quality of the facilities, the last part of JILA was built in 1981, and if you want to do ever more cutting-edge optics experiments, you need ever more stable floors to put things on. You need adequate air handling and water handling and I don't know what all. The facilities are not quite adequate right now to bring in new hires who are at the top of their game. This story has a happy ending or happy middle. We are anticipating construction on a new building. Here it is drawn in an architect's schematic. This is the current S-wing of JILA now. The tower is here, Dwayne is off to the side somewhere. This is the new addition 5-story tower at the end here. Apparently on the day this picture was taken, it was being hit by a giant water balloon. And this will have state-of-the-art facilities for us, the clean room that we need. I did not know that. Oh, we're getting all this too? Yes. Oh, okay. The rest is hidden behind, what is this? That's the dorm across the street? 50,000 square feet. Well, you've just made my day. It's even more than I thought there was going out there. Anyway, the point is this is going to do the job. Right now, we are anticipating a total cost of $37 million to build this building ready for the labs to move in and start doing science. Of that, NIST has committed $22.5 million, I think essentially by a special act of Congress or something like that. CU has contributed $9 million to this project, and we are optimistic that it is going to go forward and the ground will break next spring. And so on that happy note, I'll stop and thank you for your attention.
I'm going to tell you about our teaching and research, which is done mostly in space, but also laboratories here on the ground, telescopes on high mountains in New Mexico, and of course the Hubble Space Telescope. First, just the one slide on who we are and a little bit of our accolades. We have 22 rostered faculty and 4 research professors, 150 undergrad majors, about 50 grad students. I think it's 49 as of today, and about 30 postdocs. The last time the NRC ranked us, we were number 12 overall and number 5 among public universities. But that's a long time ago. We think we've gotten better, but we'll find out. Every one of our faculty, and this makes us kind of unique, everyone is associated with an institute or a center. And so there they are. There's JILA, which you just heard about. We have 5 of our faculty and 2 research professors in JILA, 6 professors in LASP, and 11 faculty in CASA, which is Center for Astrophysics and Space Astronomy, and 2 research professors. So everybody is linked up. They have their grants through one of those institutes or centers. What do? Well, we're the people that are in the space game. There's an awful lot of alphabet soup here on this campus, JILA, LASP, CASA, Ceres, et cetera. But anything that's, almost anything that's done with space is done in our department. We're the academic wing, ranging from the sun to planets to stars to galaxies to the Big Bang. And in case you're wondering what this is, that's the microwave background radiation from the first few minutes released after 400,000 years, but produced in the hot Big Bang. And we have a group that studies that. One page of highlights. I'm not going to brag too much about our illustrious faculty. A lot of them are here. You would probably just go to their head. So we've got some very talented faculty. But the thing that makes us unique is they're all in one department. The astrophysics, the planetary scientists, the space physicists, primarily, not all of them, are in one department. So when we reach out to undergrads or grad students and they're not sure what they want to do, we say it's one-stop shopping. We're very broad across the spectral bands, from optical and ultraviolet, X-ray, infrared, radio, and submillimeter, and very healthy groups in theory, observation, and instrumentation. We've got very, very well recognized alumni who are now on the faculties of universities, observatories, and labs. And why? Well, we think it's because we give them great training with hands-on access to telescopes, satellites, observatories, and planetary missions to just about every planet. And like all our previous speakers, I will say that we take teaching very seriously. More on that in a little bit. But how does it show up? Well, it shows up in the instructional innovations. Our department is also heavily involved in clickers, curriculum development, public talks, CU Teach, and training future teachers. Okay, I'm going to dwell on space, and not the kind up there, but the kind down here. We're running out. Fortunately, most of us are in this central unit that you just saw, the Dwayne Physics and Astrophysics building, the Gamow Tower, the JILA wing. We've got 2 labs off campus. We've got our planetarium and Summersbausch Observatory down here. And if you add it up, it's 7 different locations. So I was really pleased to hear Todd Gleason talk about contiguous space. It's really important to us. I think we're missing out on a few things by being just a little too far apart, and in particular, the stadium. We've spilled over there, but it's not the best space. We have 2-degree tracks, 150 majors, as I think I said earlier, 20 to 25 degrees per year. The last 2 years, that's been #1 in the country. We have 2 tracks. One we share with physics. Astrophysics and physics are very closely integrated. This is the degree that we tell students to go into if they're going to grad school, research careers at NASA, or observatories. And about half our students do that. The other half take what's called general astronomy track. It's still a very technical degree, a lot of calculus, physics, but also emphasis on instrumentation, computers, data analysis, and education. And I'm happy to say that typically 3 or 4 of our majors every year graduate and go on into K through 12 teaching. Some go on to science policy, science writing, ROTC, aerospace. I don't think I need to dwell too much on this. I've said it. Our students head to many careers, wherever they can get jobs. But our goal for the grad students is Research One universities and national labs. Increasingly, with our instrumentation, they go to Lockheed Martin or Ball Aerospace. A small number go to teaching at small colleges. They go straight out of a PhD into a tenure track job. Science policy and the software industry. One of the little factoids that I like is that in the last 15 years, we went back and tracked, and over 90% of our graduates are still doing astronomy, planetary science, space physics. Okay, now a little interlude. We're the ones with the really pretty pictures. I think with our colleagues in LAST, we have had instruments on missions to nearly every planet. Certainly Mercury, Venus, Mars, Jupiter, Saturn, and increasingly on beyond. There's a mission on to Pluto. Pluto's still a planet in our book. It'll get there in 2015 with some experiments developed here and also down at Southwest Research. On the astronomy side, many of you that read the papers saw the latest from Hubble, these beautiful images, and also here on the lower right, Mitch Beagelman said, I had to put a spectrum in. We built the spectrograph that went on Hubble, and this is data that was taken last week. Please no one go publish it. We're still writing papers, but it's very exciting times right now with Hubble. We have a strong theoretical group, both in JILA and in CASA, in astrophysics, that does studies of black holes, accretion, first stars, clusters of galaxies, dark matter. That's just 2 pretty pictures to give you a highlight of the kind of things we do. A lot of this is very computationally intensive, and so the connections with physics and with applied math are quite strong, and we're very pleased to be involved in the computational initiative. Space astronomy is an area that we're possibly one of the top 1 or 2 in the world for training students to build hardware. As I said, we just built an instrument that went on Hubble. We also train students to work on ground, to build instruments, to take data, to go observing. It's still a very hands-on field. So this is our telescope that we own 1/8 share of. It was about a $2 million investment a few years ago. We also, as a consortium, own part of the Sloan Survey. We own the 1/8 share of the Sloan Survey telescope. The future of this is still being discussed, but it's still a training ground and great observing for many of our best honors students and grad students. This is where they learn how to observe. And here are 2 of them on the left that have gone on to a postdoc, Molly Hicks and Stevie Fawcett. Max Moe seems to be claimed by all of us. He was just the star. I recruited him, I think, 6 years ago from Fort Collins. I still remember his mother and dad coming down, and I convinced him to come here instead of Caltech. And he did. And he got 3 degrees, 1 from us, 1 from physics, and 1 from applied math. And my picture's a little older. This is a very young Max Moe. He's now at Harvard in the astronomy program. Okay, looking to the future, the last few slides are our aspirations. We're in an area of investment called millimeter and submillimeter astronomy. It's the hottest new area where detectors and throughput in devices are increasing rapidly. Caltech and Cornell asked us to join, and we have. It's a $5 million capital fundraising campaign. It's to build a 25-meter dish, radio dish, that's an artist's conception, down in the high Chilean desert. 16,500-foot plateau. There's the plateau. And up on one of these volcanic peaks at about 18,000 feet, we want to put CCAT, high above the dry desert. Looks like Mars, doesn't it? High above the desert in the Chilean Andes. We're already underway. We've, I think, gotten 10% of the way to the fundraising, but that's our big goal. And we hope to have this up sometime next decade. So my last slide is a little bit provocative to all of us, including the deans and provosts, but us too. What is the road ahead? There's the Milky Way, and I don't know where that road leads, but for us, we want to ask the question in our self-study, do we really have what it takes as a department and as a university and as a college and as a graduate school to be and remain a top 10 department? I think we're close, and we're hoping we'll be in the top 10 when the NRC comes out. What do we need? Well, we think we need new faculty and hiring. We haven't hired in 3 years, and with this recession, I'm a little worried. We need department infrastructure to retain those faculty. We need to compete for the top students and postdocs. And I think to do all this, I'm not going to hold my breath and rely on the state. I think we need major fundraising campaigns, and we're already doing that. Most of us are fundraising a lot. And what would we spend them on? Why did I get 30 million or 40 million? We need support for the telescopes and labs. We need a new building. We're out of space, as everyone said. We need a digital planetarium. We need scholarships and fellowships for our students. And finally, endowed chair. We don't have any endowed chairs, and I'm personally appalled at that, but it's our fault. And so we need to work on fundraising and make all these things happen. Thanks.
I'm here to talk about the Department of Mathematics, and it's my pleasure to do so. Our work in education, teaching, graduate and undergraduate, our interaction with other units, our outreach, and our research, of course. These are the people that bring our department together. We have basically 4 aspects. There's the staff who form the public face. The first people our constituents, our students meet when they come in the door of the math department are our wonderful staff. There are undergraduates whom we service, and some of our undergrads even teach in the Learning Center. There are graduate students who are coming, will hopefully become the future of academe, and there are us, the faculty members. This is our mission statement. It's a little bit hard to read, small font, but the basics are, we want to be strong in our service teaching, our teaching of service courses. We want to have an exemplary major. We want to have a great graduate program, and we want to do cutting-edge research, and of course we want outreach to the community. And we want to work for the betterment of mankind like the other departments. This is a little bit of a picture of our breakdown in our faculty. We have 27 tenured and tenure track, the TTT. As you can see, 11 professors, 11 associate professors, 5 assistant professors. We'd like more. We have 1 new postdoctoral fellow, this year a Meyer postdoctoral fellow. We have 3 semester-long ULAM visitors. We have 2 rostered senior instructors and 2 rostered advisors who are also instructors. We have 12 this semester adjunct lecturers. This is our research. It looks a little bit messy there as a Venn diagram. This is because all areas of mathematics are similar, have some intersection there, alike. They all have in common the aspect of problem solving, and that's what we want to give to our students as well. We also have a lot of interaction outside the department. You can see here that many of our professors work with other departments and institutes in the university and in Boulder. I've listed them there. And we also have a lot of collaboration with universities and fellow professors both within the US and outside and internationally. We go all over the world. We love to travel. We have publications, and this is just several recent publications in the top-ranked journals by any measure, either by ISI or by MassSciNet. You name the measure you want to choose, we publish there. We are very proud of our research that we do and of the abilities of our faculty members. We have lots of books, edited volumes, conference proceedings, textbooks, research monographs, and we even have patents. This is Kent Goodrich, who with his collaborators at NCAR received a patent for the National Efficient Spectral Processing Algorithm. Not only that, but we give a lot of conferences here. We host a lot of conferences in Boulder. We were fortunate enough to host one just very recently, but we also go overseas to the conferences, to the best conference facilities in the world. There's the Fields Institute in Canada, Oberwolfach in Germany, MSRI, and our members, our keynote speakers, are at international conferences. Here's a little bit of our NSF recognition. Perhaps the largest award has been given to our new associate professor and undergraduate chair, Brian Ryder. He received a career fellowship. He also received the Rollo Davidson Prize awarded by University of Cambridge for the most outstanding young probabilist in the world. He shared this prize last year. And our young associate professors also receive NSF support. We see some recent support just received this year. And also the top, some not so young and not so recent support, but we receive it, and Nat just got a focused research grant with many universities. Even our postdoctoral fellows get NSF support. Our recent postdoctoral fellow Christopher Sinclair, just got a tenure-track job at Oregon, and he got an NSF grant in probability. He's now going to Oregon with that grant, but he did receive the grant. We get NSF money for conferences. This top one is very exciting, led by Carla Farsi, involving a lot of human resource training. Want to train graduate students and postdocs in analysis with the Great Plains Operating Theory grant, a special meeting, a very competitive program. Carla got that grant. We also got a very competitive conference grant for the BLAST series of conferences for 3 years. That's joint with New Mexico State and Kansas. We also have the Number Theory Center, which is funded by the College of Arts and Science, and that Number Theory Center also put on an NSF-sponsored graph in 2006. Now here are the conferences I was talking about earlier. Boulder is a favorite venue for conferences. We've had several of them here. Just one this past year. We were fortunate enough to have the provost open it and the vice chancellor for diversity and equity take part in it. She took part in a special lunch for women. And in addition to organizing conferences, our department members do a lot of service to the department and to the university community and the profession. I've just listed some here. The university service, the campus service here, and we contribute to the city of Boulder through public lectures and serving on panels, etc. And we contribute to the profession through NSF panels and AMS panels and committees, etc. We're very proud of our graduate program. We'd like to make it bigger, like all departments, but this year we have 74 total grad students, 17 of whom are women, 14 first-year grad students, 4 of whom are women. We have 55 of them funded by teaching assistantships. We have 2 chancellor's fellowships. You've probably heard of that, are through the generosity of the graduate school. That's the most prestigious fellowship CU can give to a graduate student. And we have had several of our students funded as research assistants by Department of Electrical and Computer Engineering GON grant, the Department of Education. Doctors Grant and Ryder have arranged for their students to be funded through that. Here is our graduate chair in the middle there, interacting with one of our Chancellor's Fellows, and that's Dr. Grant, and Dr. Farsi is interacting with one of our AGEP Fellows for graduate, Alliance for Graduate Education and the Professoriate to increase the number of underrepresented groups in the mathematics and scientific fields. We like our undergraduate program as well because it was recently revamped. It now has 3 tracks: the comprehensive track, applicable track, and secondary ed track. There you see we have a BA MA program for undergrads. There's one of our instructors, Dr. Shah, is teaching pre-calc and a big lecturer. Let's say I went to that class, great class. She's using clickers wisely, I would say. And we also are co-teaching with the Department of Ed. And we have Undergraduate Resource Center. We also train our top students to take part in the National Putnam competition. There you can see Dr. Kearns with giving them their certificates. Our number of majors has grown considerably since we hired undergraduate advisor, Carrie Muir, and we've now hired Evelyn Poix as well. And I should remark that all of our classes above the pre-calc level are taught in small sections. We also have the 4th largest numbers of undergraduate credit hours on this campus. We're very proud of that. So this was from 2007, 2008. I haven't updated it yet to 2009, but I will. You could say that mathematics is a good business proposition here. Now this doesn't include 2009 either, but our number of TTT, tenure and tenure track, has remained fairly flat over the years. Theoretically, in theory, we have 30.5 FTE, but actually, at the moment, we have 27. We do a lot of outreach. Here's our chair, Dr. Eric Stade, performing outreach. For the past 4 years, he's received outreach from the university to help out at all levels at the BVSD. And he and his wife took part in the CU Wizards program just this last year. Innovations, we're transforming calculus. We have our new undergraduate learning center, which uses undergraduate learning initiatives. Undergraduate learning center, which uses learning assistants who are undergrads. As part of the STEM learning program, our chair, Eric Stade, is the math project manager. He's going to investigate how our learning assistants are helping our calculus program and our major in general. The graduate program, we're currently in the process of redesigning both the prelim exams, and as well we're introducing some new master's program, or a new way to obtain the master's degree. Now here I wanted to say it is very good to be kind to your emeriti. Be generous to them, because you never know when they will give you some money. We have been very fortunate indeed with our kind emeriti. We received $2 million from Bernie Meyer, and that allowed us to set up our first ever Burnett Meyer instructorship. Graham Wilkin is pictured there giving a seminar. He's our first Burnett Meyer postdoc. So in conclusion, I'd like to note that our number of undergraduate credit hours has risen. The number of math majors has definitely risen a lot. The number of faculty members, or TTT, has shrunk. And our recent hires, we believe, I don't think we're biased, have been just outstanding. We're very proud of our young faculty. Therefore, our goal is to increase to 31 TTT by the year 2015. And corresponding to that, of course, we want to increase our graduate program. We want to have 90 students by the year 2015, but of course, like all other departments, we need some place to put them. We're running out of room. We got 20 emeriti in one office. Not all at the same time, of course. And our postdoc program, we've passed one through this most recent postdoc. It was extremely successful, got the grant, got a tenure track hire in this most difficult of hiring seasons at University of Oregon. And also, we do not have an IT technician. That's something we would definitely like by the year 2015. At the moment, we had an assistant professor doing it for a while. Now we have one of our associate professors who's involved in the computers. Since they're so essential for mathematicians and for everybody, we really would like an IT specialist. So I thank you for your time. talk to you afterwards.
Well, good afternoon. I see we didn't compete so well with this nice weather. I wish we would have done better. I'm going to give a talk that's going to be real plain vanilla. Todd, I'm not selling at all. I'm not selling at all. And the reason I'm not selling is because I really want to focus on the questions that are really the part of this faculty forum, and that is, how are we going to work together? The units are going to work together. Where are we going in the future? And what is the vision? I'm going to share some key statistics of this department, and then I'm going to talk about what it is we're doing and what we see. Committees we formed to start to explore that vision. But I think in the end, what chemistry and biochemistry will do will be to request a dialogue about opportunity and about the opportunity that we see and how we want to invest in those opportunities, or we don't. There's limited resources, I think, going forward here in the next couple of years. So I'm not going to tell you how many tenure track lines I'd like to see. If you give me a blank checkbook, I'll ask you for as many as I could fit in any one space. But we are going to talk about programmatic decisions and things that have to happen. Now, my unit is arguably one of the most complex on campus, and it is going to get more complex. And the reason it's going to get more complex is because we are going to move half of chemistry and biochemistry to the East Campus. And when we do that, you can imagine the strain that'll put on the faculty and the infrastructure and so forth, the resources in the department. And clearly we will address that in our program review. But the department is a pretty strong place, and we have fantastic faculty. And it wasn't as if I couldn't think of other things to do with my time, actually, than be chair. I did it because I really believe in our faculty, and they're worth that extra amount of work. So just to point out a few of our distinguished faculty, and I don't want to belabor it because, well, okay, we had 3 NSF Career Awards last year. We've won the Governor's Award, Bob Seavers did for research. But I could go on and on. I could do this I could fill the slide, but I don't want, that's not the point. The point is that in this slide, Tom Check at the top, the first Nobel Prize winner in Colorado, also came back from the best science job, arguably the best science job in the world, running Howard Hughes. And he came back because he believes in CIMB, he believes in this department, and he believes in what's going to happen in the future. And not only is he back to run CIMB, he's teaching honors freshman chemistry right now. That's a pretty strong commitment, not just to research, but education. And Tom really, really sets the tone for the department. He really shows tremendous leadership by example, which is not easy when you're as busy as he is. Marv Carruthers, Carl Leinberger, Joseph Mickle, Bob Seavers, Maggie Tolbert are all National Academy Science members. Marv Carruthers donated $20 million to the new biotech building because he's a very successful entrepreneur and he can afford to do that. And because he loves the mission of biotech and the idea that we're going to build something great in Colorado, which we haven't quite done yet, turns out. And the interesting thing about this list, if you go down it, this series of distinguished faculty members, and all of these are National Academy members below Tom, it starts out with Marv being more chemical biology, Carl being physics and being part of JILA, Joseph having interactions with JILA and being physical chemistry as well as organic, Bob Seavers being analytical, and also more recently being recognized for his work on inhalants for vaccines to be used in the third world. And then Maggie Tolbert in atmospheric and environmental, and she's an important part of CERES as well. So our faculty, and this is just a few examples, are heavily involved in a lot of the initiatives in the institutes on campus, in some cases having major leadership roles. So let's get to some of the numbers for, what does this department look like? We have 45 tenure track faculty. Right now we have 3 senior instructors. We have a number of lecturers and so forth. It's a fairly large department. Enrollment per semester is over 3,000 students, not hours, but students enrolled. Number of majors, 601. We're up 36% over the last 5 years. BA degrees conferred in 2008, those are numbers that we have, 91. And then total student credit hours taught by tenure-track faculty, 11%, up 11%. So we are not making the decision in our unit, and we're not going to make the decision to have more and more lecturers. We want the research-active tenure-track faculty in the classroom, and we want to support that going forward in any review document. And keeping going on these statistics, it's a large department overall, including faculty, staff, graduate students, and postdocs. Current numbers, and these are actual numbers, 390 is the size of this department. PhD students, 207. And we are number 4 on campus for research awards. That's after Series, LASP, and JILA in that order. And we are the #1 department on campus, and not by a significant amount either, in research awards for 2008, and we're doing real well this year too. 113 awards overall, totaling a little over $14 million. So, an important statistic here is that our undergraduates go on, 80% of them to pursue advanced degrees, and that could include going to medical school as well as graduate school and other professional degrees. But also 10% of them end up staying in the state and be an important resource for the state. So from Todd's perspective of planting seed corn, we're planting about 10% of them here. I think the other 90% are being planted elsewhere. One of the things that we really want to see happen, and I think this is chemistry being coupled to the institutes, the initiatives, and how they're related to energy and the environment and healthcare through CIMB, that we want to become more relevant for commerce in the state even. Not that we don't love basic research. I love basic research as much as anybody. I really do. But I think there's an entrepreneurial spirit and a genuine desire to really contribute to this state and its future. So just to give you some more data, that our overall ranking nationally is 28th. Okay, so that's consistent with Todd's comment. We're close to the top quarter, in the third at the very least. You can argue about exactly where this is. But biochemistry ranking is 13th, and physical chemistry is 9th. And of course, we've benefited in physical chemistry from JILA and those associations. And so this really begs the question, and I think this is where PRP is headed for chemistry and biochemistry. Clearly, the Department of Biochemistry and Biochemistry can build on its strengths and to continue to improve in its national and international rankings. And now, building on its strengths doesn't mean maintaining its strengths and just doing the same things we've been doing. It means to do some new things. And I want to talk on my final slide, and I'll even be right inside the time limit, I'm sure, is really how we're going to do that. So how will the department evolve? And we're going to have closer ties with the institutes and the initiatives. That's how we're going to grow and evolve. We already have close ties with CIMB. That's the biotech initiative. More faculty, or their faculty lines came from CIMB or in biochemistry than any other department, including mine, actually. RACI, the energy initiative, that's going to be very important for us. Collaborations with NREL, increasing our collaborations with NIST and JILA, all are going to be very important for us. And then I forgot to mention, and I should, but with CIMB and MCDB, Molecular and Cellular Developmental Biology, we have a lot of sort of joint seminars and supergroups and all kinds of activities, and that's going to continue to prosper and do well. And then finally, on the environmental side, I think we'll become involved in the Geosciences Initiative as it starts to move forward in terms of the environmental and atmospheric chemistry components of that initiative. Bill Lewis and Coney and I have had some discussions, and we're serious about this, especially on atmospheric and environmental. And we put together a series of different committees within my department to start to develop the curriculum to shoot for having the #1 environmental chemistry program in the country. And that's our goal. What am I asking for? I'm asking for you to listen to the arguments about why we should have the #1 program and how we might achieve it. That's what I'm asking for. So I want to see that we move forward on that agenda, and space is an issue and all those things. Todd, we are doing horse trading already. We are trying to figure it out. What's the best use of the space? How are we going to do that? And the top of my list, at least, is environmental chemistry and atmospheric science, with emphasis on environmental chemistry. We have some outstanding young faculty winning all kinds of awards in that area right now. We'd like to support them and grow that program. Right. So the new interdisciplinary graduate programs for us are going to be chemical biology, which we have a group of people that are coalescing. With Tom's return, Tom Check's return, Marv Crothers is being more active these days in his research program, and there's a whole host of us. We hired Charlie McHenry from the medical school, who's very active. We're going to build chemical biology in an important way. Andy Phillips, who just came back from the Broad Institute at Harvard, which is arguably the strongest chemical biology program in the country, he came back from a sabbatical at the Broad, and he's the chair of that committee to start to define that curriculum for us and really to build the program, to start to recruit graduate students in that area, and so forth. The Materials and Nanoscience program is underway. We recruited successfully last year. We've got a number of really outstanding faculty that have really now coalesced across traditional divisions to generate that new program. And then I already touched on environmental and atmospheric. I think woven together, those three interdisciplinary graduate programs actually define sort of a hub of success for the University of Colorado, but also for the state of Colorado. These are agenda items that are on everybody's mind, where chemical biology would affect human health. Material and nanoscience will probably focus mainly on energy and alternative energy and clean energy sources. And environmental and atmospheric will make sure that we're right about all those other things, hopefully. So thank you. I'm sorry. Next time, I promise I'll have more pictures than you can stand. But.
Hello, I'm going to talk to you about the Department of Atmospheric and Oceanic Sciences. So this is a new but also an old area in the campus. There were atmospheric sciences people here in the 1950s who played a role along with other people in what's now APS in starting NCAR. But this became an independent thing on campus in 1997 when the program in Atmospheric and Oceanic Sciences left APAS. And we came to the department in 2005, and we really only got separate degrees from APS in 2008. So logistically, we're new. There are 14 faculty, 13 tenure-track faculty in ATOC at the moment, so it's much smaller than the other units you've heard about. And we have a wide distribution amongst the institutes, so historically we've been heavily involved with Ceres and LASP. And these little halves indicate that we've invested a half a line from arts and sciences with a half a line from an institute to hire a faculty member. Our latest hire was an InStar, and we've also made a new hire who's entirely in arts and sciences that's in the Energy Institute, RACI, as well as being a co-hire with NREL. And then we have a research faculty member with NCAR and several people who are just in arts and sciences. So we're heavily invested in all of the institutes that are in the sciences. In addition, we have affiliate faculty that are involved from chemistry, for example, geography, and several other departments. So we interact with the other departments as well who take our students and we swap students with. So it's very interdisciplinary. So these are just some of the areas that we're working in. We have 3 oceanographers. May surprise you to learn that Boulder has the 3rd largest concentration of oceanographers in the country after Woods Hole and Scripps. So we have a very active physical oceanography program. We have an atmospheric chemistry program that involves atmospheric sensing. There are 2 people in ATOC. There's 3 others in the chemistry department and some in InStar. It's a campus-wide thing. There are people working in clouds. These are deep convective clouds, which also involve people in other departments. We have people interested in the upper atmosphere. For example, Cora Randall is the PI on an instrument for a satellite that's currently in orbit. We have another PI over here, Peter Paluski, who's working on a satellite to measure the solar output, which will be launched in a few years. So we have 2 satellite instrument PIs in the department. We have people who go to the polar regions, study polar climates. We do a lot of numerical modeling, so we have an interest in working with applied math, for example, on large numerical models. We also do fundamental fluid dynamics. We have a new investment in wind energy, so we have someone studying siting wind farms and how do you make wind farms more efficient and things like that. And then we have a young woman who likes to go stand in the middle of hurricanes and chase tornadoes around to look at severe weather. So the department has chosen to be very broad and to approach a wide variety of areas, and that's because there's 2,000 atmospheric scientists in Boulder. It's the largest collection of atmospheric and oceanic sciences people in the United States. So there's great depth in any area in Boulder, and by investing in a wide variety of areas, we can send students out to NOAA, NCAR, and a wide variety of other places. There are companies here like Cora, Colorado Research Associates, which is a large company with a lot of fluid mechanics people in it. There are a number of private forecasting companies, and then there are all these other people on campus who work in this area. So our goal is to interact with large numbers of people and attract large numbers of students. There aren't very many things that have ranked atmospheric sciences. On the left is something NCAR put together 5 or so years ago about geosciences, and if you can read down that list there on the bottom listing here, that's the numbers of papers written in the geosciences. You see Russian Academy of Sciences, NASA, NOAA, Geological Survey, Chinese Academy of Sciences, University of Colorado. The University of Colorado is the most productive university in the world in geosciences. If you look up here at citations, somewhere something happened to the Russians and Chinese. They disappeared out of the top 10, leaving NASA, NOAA, NCAR, Geological Survey, and University of Colorado, which is, again, the leading geosciences citation effort in the United States or in the world. So the University of Colorado is a place to go in geosciences. Of course, this isn't just ATOC, it's Ceres and INSTAR and LASP and geography and geology and many other units. There are only one ranking I know of in the last decade in atmospheric sciences, published in the Chronicle of Higher Education. It only ranked 4 areas at the University of Colorado in the top 10, which were geography, aerospace engineering, atmospheric sciences, and oceanic sciences. So at least in that ranking, this is the best one, of course, that exists of all the rankings that have been cited. ATOC is half of all the top 10 areas at the university. And we rank both in atmospheric sciences and in oceanography. So we'd like to move up into the top 3 or 4 instead of just hanging out in the lower part of the top 10. Numbers of graduate students have been rising steadily with time. We now have about 70 graduate students. So for example, we have half the faculty of APS and 50% more graduate students. And this is largely because lots of people like our graduate students, so they go over to other departments and up to NCAR and NOAA, as well as working with our faculty. Our credit hours are continuing to grow here. We teach about 9,000 credit hours, which of course is a lot less than the other unit you've heard about. But on the other hand, we don't have near as many faculty. So our average faculty member is now teaching 800 or 900 credit hours a year, which is probably higher than any other unit on campus per faculty member. And we have 6 or 7 graduate students per faculty member, which is probably also higher than any other unit. We're also a relatively diverse department. We currently have 7 men and 6 women. So it's probably the most diverse gender-wise department in atmospheric sciences in the United States, and probably the most diverse science department on campus. We have 2 minority faculty. Our graduate students are about 11% minority. And the surprising part about that is if you look at what kinds of minorities they are, they're largely Hispanic, whereas most atmospheric science departments tend to have large Asian components to them in the United States. So we're slightly different in that regard. Our faculty numbers have been static for the last decade. So this total faculty numbers, which peaked in about 2000 and fell for various reasons and have almost recovered now. So this is recovery is partly because the graduate schools invested an extra 1.5 faculty members here. We have 1 unfilled line here in arts and sciences, which should, if we ever get to hire again on that, put us half a line above where we were in year 2000. But basically we've been static. So we've done a lot of growth in graduate students and in every other credit hours and everything else, with no growth in faculty, like every other unit here. Okay, so what can we do to make ATOC even better? Provide contiguous space, including labs. I always like to compete with APS since we came from them. Mike showed they were in 7 locations, we're in 9 locations. So we've only got 13 faculty, we're in 9 locations. This is somewhat challenging to have a faculty meeting. We obviously would like more faculty. We're probably the smallest atmospheric sciences department of note in the United States, which makes it hard to compete when other people are 2 or 3 times as big as you are. And we have a very small staff, which is the same story we've heard from everybody else. So in summary, we're young, and we have a young and diverse faculty. We're already recognized nationally in the top 10 in both atmospheric sciences and oceanography and what rankings there are. And we have a natural advantage here because there's an immense Boulder community in this area. So there's a very great potential here for growth in this unit and further interactions with NOAA and NCAR and other parts of the Boulder community. And we already have a large and successful graduate program as well as very popular undergraduate classes. So we're also teaching large numbers of students. Thank you.